Introduction to Matter. Over the next few slides, I'm going to give you a very brief overview of the nature of matter, or at least the foundational principles that you'll need to know for this class. If any of this information seems unfamiliar or unclear to you, maybe your some other introductory science class didn't stick in your head very well. Maybe that high school chemistry class was 15 years ago. Whatever the circumstances, if you need more clarification, I'll have additional videos posted on Blackboard, links to like Khan Academy and stuff that can help you get up to speed. So starting off here, matter is anything that has mass and takes up space. Mass is the amount of stuff, basically. And more specifically refers to the number of atoms, or the weight, which is a function of how much stuff there is, how many atoms of a given kind there are in a sample under the influence of gravity. That's what weight is. In practical purposes, though, we measure mass as weight in a regular classroom, or you measure your own bodily mass by stepping on a bathroom scale. Volume is how much space something takes up. So how spread apart the individual atoms or molecules in that thing are, or how tightly packed they are. The amount of space that they take up is what volume is. Density is an intensive property. So this is derived by factoring both the mass and the volume. How much mass did you cram into a space? So here you have an illustration. You have red spots here each represent atoms with a mass of 1, and they're in, I'll just pick a different color for now, this much space. If you have less stuff in the same amount of space, the density is less. The stuff is packed in less tightly into that space. If you put more stuff into that space, the density is higher. The stuff is more tightly packed. And similarly, if you pack the same amount of stuff as the first example into a smaller space, the density will also increase. In other words, density is a function of both mass and volume. As mass goes up and volume stays the same or goes down, density will increase. As mass goes down and volume goes up or stays the same, your density will decrease. A reminder that since this is a science course, we're always going to use metric terms. I'm not going to use miles per hour. I'm not going to use pounds. I'm not going to use inches. We're going to use metric units. That's centimeters generally, or meters for length, grams or kilograms for mass or weight, liters for volume. Density, I told you that's a function of mass and volume, is mass over volume, grams per liter. So for every number that you give, you're going in science, you're going to also need to declare units. So if you just say that something is 48, that doesn't mean anything, right? 48 what? You always have to declare your units, even when you think it's obvious. So remember, if you're saying how long something is, you'll say it is 146.32, what did I say? length, okay, meters, kilometers, or 73 grams. Or if you're talking about density, 1.26 grams per liter. Here we go. The smallest type of matter with its own identity is an element, and the smallest particle of an element that can exist and still retain that element's properties is an atom. So really, an atom is the smallest type of matter on Earth. An atom is made up of protons, which have a positive charge, electrons, which have a negative charge, and neutrons, which have no charge. Atoms, the nucleus of an atom is made up of protons and neutrons, and electrons, quote unquote, revolve around the nucleus. Now, you've probably seen in chemistry class or something the little diagram where you have like your protons and neutrons and stuff in the middle making up your nucleus, and then you have shells, like valence shells surrounding the nucleus. That's a super, super, super effective model for how an atom works. But in reality, it's more like the electrons revolve around the proton or the nucleus in this sort of cloud. They can spin around in all kinds of different directions. And they ultimately make what's referred to as an electron cloud around it. So you have your protons, your electrons, and your neutrons. Your protons is what determines what element an atom is. So you can change the number of electrons and the element is still the same. It might be negatively charged, more negatively charged than before, or more positively charged than before. If you add electrons to an atom, it'll be more negatively charged and it'll be called an anion. You're going to turn that atom into an anion of that element. If you take away electrons from whatever its base state would have been, it'll become a little bit more positive, and those are called cations. You're going to make that element or that atom a cation of the element. You can change the number of neutrons without changing what the element is. So you can change the number of electrons and the element is still the same. Change the number of neutrons and the element is still the same. Adding, actually, since I used that for positive charge before, I'll use this. Adding neutrons increases the mass of the atom because they are physically substantial things. Protons and neutrons have an appreciable mass. Electrons don't. Their mass is so small, even in comparison to the mass of a proton or a neutron, that it's borderline negligible. So if you increase the number of neutrons, you'll increase the amount of mass. That also increases, assuming you're going over and beyond what the natural state is, increase instability, and therefore increase radioactive potential. Whenever you're talking about an element decaying, like uranium decaying into lead, it gives off radiation. Uranium is a big atom with lots and lots of neutrons. It's in its natural form, it's very unstable with all those neutrons. And so it's slowly kind of shedding these neutrons and some energy along with it. And that energy release is radioactivity. Ultimately, uranium gives off radioactive energy until it becomes lead. And that's kind of its base, most stable state. If you change the number of protons, though, you're going to change what the element is, flat out. So the atomic number refers to the number of protons in an atom, and therefore, those three dots in a triangle means therefore, tells you what element you have. Your atomic mass is how much your atom weighs. Oftentimes, especially for small atoms, they're basically the same. If you assign a mass amount, an atomic mass of 1 to a proton and an atomic mass of 1 to a neutron, which we do, and electrons are tiny, 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 they're negligible, then however many protons plus neutrons you have is how much your atom weighs. Typically, this is going to be double your atomic number. The atomic number tells you how many protons an atom has, and especially for those small ones, you can typically just multiply it by 2, and you'll find out what its baseline atomic mass is. A compound is some sort of molecule with 2+ elements, or some sort of substance with 2+ elements mixed together in some sort of chemically bonded situation. This requires chemical bonding. A mixture is just sort of a hodgepodge of atoms in the same place, in the same space, but are not chemically bonded. This includes molecules. So a molecule is any kind of arrangement of more than one atom. If that molecule features more than one element, if you feature a couple different kinds of elements, then you have a compound. If you have a bunch of different types of atoms or molecules all mixed up in the same place, but they're not necessarily bonded to one another chemically, then you have a mixture. An example of a molecule that is not a compound would be O2, regular environmental oxygen. There's 2 oxygens bound to one another chemically. You can see the 2 means there's 2 of them. But there's only one type of element, so it's a molecule. A compound would be something more like this. C6H12O6, which is sugar. Which sugar, you might ask? Glucose, fructose, sucrose. They're actually all the same. It's just a matter of how you arrange the atoms that gives it slightly different properties. Some of the sugars are simple sugars. Some of them are disaccharides. They're 2 sugars put together, but really it's the same atoms that are just shuffled. A mixture would be like a solution of H2O and C6H12O6. So sugar water. The sugar will dissolve into the water, but it's not actually going to bond with the water. You're not going to make a whole new substance that doesn't have anything to do with water or sugar out of this, right? It's really just kind of be a mixed up solution of sugar and water. So this is an example of a mixture. When you're writing out these chemical formulas, you're going to use the chemical symbols given to you in the periodic table of elements. So hydrogen, which has 1 proton, has 1 proton. So its atomic number is 1, equals 1. Its mass is 2, and the symbol is H. I'm not going to get into any kind of bonding rules in this lecture, but I'll post a video, a short lesson about it in case that's something that you need to fill in some gaps in your brain to understand this stuff. Other ones that we'll commonly come across frequently, and especially a life context, a biology context, so we have hydrogen comes up all the time, carbon, nitrogen, oxygen, chloride, sodium, those two make up, or chlorine and sodium, that makes up table salt, calcium, iron, so forth. In a forensic standpoint, you might also come up with other things that are related to metals. So like this is, again, that's iron. There is, where is it? Copper. We have lead. You'll find lead from time to time that'll come up. Those are the symbols, and that's what the atomic number refers to. Finally, we'll talk just briefly about the different states of matter. You should probably be pretty intuitively familiar with this from just like cooking and things like that. So your basic physical states are solids, liquids, and gases. A crystal is a solid with a regular repeating molecular pattern that dictates its shape. So if you have a solid that you have custom made into a given shape and doesn't come in any kind of a consistent shape with consistent angles to it, that's going to be your regular old solid. It might be made of one element. It might be made up of lots of elements. It kind of depends on what it is that we're talking about. If you have a solid where you have a regular repeating molecular pattern, the same molecules in the same arrangements over and over and over and over, that's going to create really specific shapes. We can exploit those regular repeating shapes to refract light at in certain ways that, in certain predictable ways, I should say. We've talked a little bit about that with polarization in the polarizing microscope. You put a crystal in there, you know how that crystal is going to refract light in a very specific way. And depending on how you turn it and how you examine it, you can look at different properties of the thing that you're trying to see. A regular old solid, where the constituent atoms or molecules are arranged in like a random or disordered pattern, is a amorphous solid. So usually when you're talking about a regular old solid, it's probably amorphous. A liquid takes the shape of its container. And its atoms are less densely packed than solids. Gases will also take the shape of its container. Solids have their own shape, right? Gases will also fill whatever container it's in. It'll ultimately take the shape of its container. And the atoms are more spread out than solids. So this would be decrease of density for each of these. To change the physical state, you can either add energy, delta state, change of state, energy, or take away energy. By taking away energy, you're going to move from more energetic states to less energetic states. Gas floats pretty freely in the atmosphere. You have the atoms that are just sort of floating around willy-nilly, relatively low density. It'll fill up whatever space it's in. In order for atoms to be that sort of loose and suspended from one another, they have to have a lot of energy. Forms of physical objects that have less energy are going to ultimately go down to more of a solid state. So if you add energy to a solid, you can melt it and it becomes a liquid. You can do this by just putting a candle up to an ice cube and melt the ice cube. Some things like metals, you might need to blast it in a furnace of thousands and thousands of degrees. But you can turn any solid into a liquid if you apply enough energy. You can apply more energy still to the liquid and evaporate it or vaporize it, and it'll become a gas or a vapor. Vapor usually refers to water suspended in the air, and any other liquid that's evaporated, it can be anything. So this is a high energy state, and this is low energy. Conversely, if you take away energy, you can turn a gas and condense it down into a liquid. Take away more energy still, and it's called freezing that liquid into a solid. Any liquid can be frozen provided that you have a cold enough environment. Temperature refers to the amount of energy behind molecules, basically. So whenever we're talking about adding or subtracting energy, we can also be talking about increasing or decreasing temperature. It's important to remember that through all of these states, all of these physical states, the name of the compound remains the same. Unless you go and add something else to it, the solid form of water is still just water, the liquid form of water is still just water, and the gas form of water is still just water.